This video is to make up for the lecture that we missed on Wednesday due to the fire alarm. And I want to talk about a couple of things that are a little bit different than box plot and ordered data before we get to that. And the first one is called Chebychevs Theorem. And this is a nice theorem that tells you kind of a worst case scenario for how much data is in the middle of a data set. So what it says is that for any data set, at least, well, I'll tell you what k is in a second, but 1 minus 1 over k squared, and converted to a percentage of that data set, is within k standard deviations of the mean. And this only works for k greater than 1. So you can see what's going on here with some examples. So if we're talking about 2 standard deviations from the mean, so we have, if this is our number line, and here's where the mean is, then here's the mean plus 1 standard deviation, here's the mean plus 2 standard deviations, here's the mean minus 1 standard deviation, here's the mean minus 2 standard deviations. So Chebychevs theorem tells us that within this, there has to be at least 75% of our data set. So it's 1 minus 1 over 2 squared, so 1 minus a quarter, which is 3/4, and that's 75%. So within 2 standard deviations of the mean, for any data set, no matter how wonky it looks, you're always going to have 75% of your data. And if k equals 3, you can play that same game. Now, rather than 1 over 4, here we're going to have 1 over 3 squared, so 1 over 9. So 1 minus a ninth, there's 8/9 left, converted to a percent. That's 88.89% roughly. So within 3 standard deviations of the mean, on either side. So within here is at least 88.89%. There could be more, and in fact we're going to see when our data sets are nice and symmetric, in fact, and they have a nice bell curve, it's going to be much more data within 2 and 3 standard deviations. If we have a nice bell curve, then roughly 95% of the data is going to be within 2 standard deviations, and roughly 99.5% of the data is going to be within 3 standard deviations. But for any wonky distribution that you like, no matter how wonky it looks, if you had a histogram that looked like this, for example, it doesn't really matter, some wonky thing, and let's say the mean for that was about here, you know that within 2 standard deviations, this has to be greater than or equal to 75%. This goes no matter how wonky your distribution looks. So that's Chebychevs theorem. A little example for this, how we can see this in action. So imagine you write a scholarship test, and on this test, 10% of the scores will get the scholarship. You know the following things. You know the mean of the test is 63%. They tell you the standard deviation is 5%. And you're told that the scores are symmetric about the mean, but they don't tell you the shape of the histogram. So maybe it looks something like this. Here's 63%. So maybe it looks roughly something like that, where it's symmetric on both sides of the mean. It's not skewed. It's kind of a mirror image on the left and the right. But you're not told about the shape, so maybe it looks, I don't know, like this. Could look like that. There's 63 roughly. And that is, I'm trying to draw these like a mirror image. That's what I'm going for here. Or maybe it looks even wonkier. Maybe it looks like this. Who knows? We don't know. But we do know that it's symmetric about the mean. Okay. And we score a 71% on this test. Is it possible that we're a scholarship winner? Well, let's use Chebychevs theorem here to figure this out. So by Chebyshev, we know that we're going to have at least 75% of our data within 2 standard deviations of the mean. So I'm just going to pick one of these distributions to draw it. And I'll just pick the bell-shaped one since that's pretty common. So we're going to get a distribution that looks something like this. And we know by Chebyshev, just from before, that 2 standard deviations from the mean on either side, if here's the mean here, within here is going to be 75% of our data. Oop. At least 75%. Now remember that this distribution is symmetric about the mean, so we know that the remaining data is split up evenly on either side. So we have 75% of the data here, so the remaining bits should add up to 25%, and that needs to be split in 2. So on either side, we have 12.5% of the data. So 12.5% of the data is above 2 standard deviations from the mean, and 12.5% of the data is below 2 standard deviations from the mean. And we know that because we're told that for this particular distribution, scores are symmetric about the mean. If you don't know that, you can't say it's split up evenly. But we do know that. Well, what are these values here? So we know that the mean is 63, and we want the mean plus 2 standard deviations here. So this is going to be 63 plus 2 times the standard deviation, which is 5, which is 73. And similarly on this side, 2 standard deviations below the mean. That is 53. So we know that at least 75% of our tests got a score between 53 and 73. And where are we? Our 71%, well, where's that on the number line? Here's 53, 63, 73, so we're somewhere here. There's our 71. So we're within that middle 75%, so there's no way. Here's the scholarship winners here. I'll do that in blue here. So here's the scholarship winners, the top 10% of our data. Are those guys. But there's no way we're in there because we're in the middle 75% of the data because of Chebyshev. So can we possibly be a scholarship winner? No. No. By Chebyshev. We are in the middle 75% of our data. So there's no way we can be in the top 10%. And that's a good example of how you can use Chebychev's distribution to help you out. And remember, Chebychev's theorem holds for any distribution, which is very, very powerful. You can use these ideas for any distribution you like. Again, it's a worst case scenario. A lot of times you have way more data than 75% within 2 standard deviations, or way more data than 88.89% within 3 standard deviations, but it gives you a worst case scenario, a lower bound on the percentage of data within those bounds. One thing we didn't cover, and I just want to talk about it quickly, this will come up in lab, stem and leaf plots. So just another way of organizing numerical data. And one thing you can do is you can take numerical data and you kind of organize it by place value. So you kind of take maybe the biggest place value, and that'll be the stem. And we look here, and we have a range of something like between 3.1 and it looks like 6.1 looks like our biggest. So we have things that start in 3, 4, 5, or 6. So our stems here are going to be our ones digit, and our leaf is going to be our tenths digit after the decimal. And this can be modified depending on what data you have. If you had, say, instead of 3.5, 4.7, 3.1, you had data like 35, 47, 31, then maybe it would make sense for your stem to be the tens digit and the leaves to be the ones digit. But here, it makes sense to let our stem be the ones digit and our leaf be the tenths digit. So we look here and we have stems of 3, 4, 5, and 6. And so what we can do is we can just write down the leaf kind of on the right-hand side for each of these measurements. And that gives us a nice way of organizing our data. So we have the first one is 3.5. So I'm going to put a 5 there, 3.5. The next one is 4.7. So we'll put a 7 there. 3.1. So I'll put a 1 here. So this row here represents 3.5 and 3.1. This row represents so far 4.7. And we can continue just like that. 3.3, another 3.5, 5.1, 5.5, 4.1, 4.7, 3.9, 6.1, 5.7, 3.8, 3.7, 4.2, 6.0. And not always, but a lot of people like to rearrange this to go from least to greatest. So we can kind of do the same thing. And before I do that, let me tell people that this is the ones digit and this is the tenths digit. So we can rearrange that for each of the rows here, just from least to greatest. So we have a stem of 3. So we have a 1, that's the least, and then we have a 3. And then we have 2 5s, and then we have a 7, an 8, and a 9. For the 4, we have 1, 2, 7, 7. 5 is 1, 5, 7. And 6 is 0, 1. And you can see that this kind of looks like a histogram as well. If you rotated this, instead of being the bars being horizontal, if you rotated it and the bars were vertical, it would look like a histogram. And this is kind of what it is almost. Everything in here is a bar representing from 3.0 to 3.9. This is 4.0 to 4.9. This is 5.0 to 5.9. So it kind of looks like a little histogram bar. So maybe it would look like this: 3, 4, 5, 6, and this would go up 1, 2, 3, 4, 5, 6, 7. I'll just kind of cheat and just write a 7 here to say that it has a height of 7. This has a height of 4. So there are 7 elements here, so the height of this histogram would be 7. There are 4 elements between 4 and 5, so 4 point something. So the height is 4. And similarly, we have a height of 3. And between 6 and 7, we have a height of 2. So you can see how stem and leaf plots look very much kind of like histograms, except you kind of keep the data along with it. Now let's get to talking about box plots. So one thing that's important with box plots is being able to interpret them, especially comparing two box plots. So we have this study here that was done in 1982 by Dunn and Master, and what they did is they recorded the recall time of pleasant and unpleasant memories, and then put that data into a box plot. So the recall time here is in seconds, so they were asked to recall, say, a pleasant event, the participants, and it looks like the participant that took the smallest time to recall that event it took them just about a second, and the time it took the person the longest to recall a pleasant event looks like just above 6 seconds. For unpleasant, it looks like the smallest time was about 1.5 seconds, maybe a little bit higher than that. And the longest time it took for an unpleasant memory, it was just over 11 seconds, it looks like here. And then the median for these data sets, this is just below 3. This is probably about 3.75, 3 3/4, etc. So that's what this data is showing. So let's talk about the differences between these two data sets that we can glean just by looking at their box plots. So things to look at are location, spread, and we can even talk about outliers. So there's some good things to talk about. Skew is another one. So let's look at location. So it looks like the data for pleasant memories is lower on the scale than for unpleasant memories. It looks like the middle 50% of the data set is in fact below the median for unpleasant memories. So it looks like, in fact, that there's an appreciable difference between the time it takes to remember something pleasant or unpleasant. So it looks like the data is kind of all shifted down. You can kind of do it piece by piece of the 5-number summary too. The max is lower in pleasant memories. The upper quartile is lower. The median is lower. The lower quartile is lower. And even the minimum element is lower. So one thing we can say is location, pleasant memories, have shorter, or seem to have shorter, I guess we could say. Seem to have shorter. Recall times. And again, we can see that by just what I said. If we needed to write a little more, we could say the numbers in the comparative 5-number summaries are lower in the pleasant data than in the unpleasant data. Well, let's talk about spread or variation in the data. Well, looking at this, it's clear that unpleasant memories have a larger spread. Both the middle 50% of the data is wider in unpleasant memories than it is in pleasant memories, and the entire data set, including the most extreme 25%, is wider too. So we can say that unpleasant memories seem to have more variance, or let's say more varied recall times. They're more spread out. So that's something we can say. Another thing we could say is about skewness. Well, it looks like that for the unpleasant data, it looks like the data is kind of bunched up here. It looks like it has a tail in the unpleasant data. So let's kind of convert this to a histogram, or at least a reasonable facsimile of a histogram. So we know that we have, I'm just going to put the 5-number summary kind of in. So there's the min, the lower quartile, the median, the upper quartile, and the max is, say, way over here. So remember, in each of these sections, we have 25% of our data. So if I was to draw a histogram with this, I need to draw it so that each of the bars would have 25% of the data, or each of the sections would have 25% of the data, which would mean, I'm going to make the bars uneven here, but that's okay. This is just a sketch anyway. But maybe you would have your histogram looking something like this. Since there needs to be the same amount of data in each section. So we can see that the data looks like it has a tail here, so it's skewed to the right. So it has a right skew, or a positive skew, skewed towards larger values. And let's convert this one to a histogram as well. Same idea. So I'm going to draw the 5-number summary, or roughly approximate it. There's the lower quartile, the median, the upper quartile, and the max. And again, 25% in each section. So this bar is going to be taller. And then this is going to be the shallowest bar, and these ones are going to be roughly, this one's going to be a little bit taller, the first one. So maybe we get a histogram that resembles something like this. Again, it's only a sketch, but I'm trying to draw it so each of these rectangles has equal area, and that gives us kind of the shape of our histogram. So you can kind of convert between histograms and box plots roughly, at least the overall shape of them. So this guy is definitely not as skewed. It might be a little bit right skewed. It seems to have a little bit of a tail here. You can see it by having kind of a long whisker on the right, but it's not as skewed. So we can say something like right skewed, but not as much as above. So maybe something like that. So we're able to discern features of the data set just by looking at the box plots. We can compare them. In fact, we can say it looks like pleasant recall times are less varied and shorter than unpleasant recall times. And it looks like unpleasant recall times have this long tail where there is some data kind of skewing where the mean would be. The mean recall time would actually be shifted over here because of this long tail. It'd be shifted to the right of the median. So we can say something like that when we're comparing these two data sets via their box plots. Now a quick note about extreme values, or what they're called outliers. That's the statistical jargon for it, outliers. And they're observations that are really far away from the mean or median, or kind of the rest of the data in some sense. They're either really large or really small. And saying really large or really small, that's kind of fudging it a little bit. What does really large and really small mean? And there's no fixed definition here. But a common definition is if you're talking about box plots, then any data point that's 1.5 IQRs or farther away from the box of the box plot, we've seen that in a previous video, they're what we consider too extreme to call normal values or usual values, so we'll call them outliers. I'll just mention this here. We'll talk about this a little more later in the course, but in these bell-shaped distributions, things that look like that, if you're more than 3 standard deviations, some people say 2, and really you have to decide what your cutoff is, but somewhere between 2 and 3 standard deviations, if you're too far away this way, then we would consider those unusual. And again, we'll talk about that later on in the course, but just as a little note, the star here for both 1.5 IQRs and z-score greater than 3, definitions vary for that. So this is pretty much what the book talks about. So I just told you those. Now, when you do have an outlier, what are the reasons for it? Well, there are a few. Maybe when you were collecting data and you were measuring things, maybe you measured it incorrectly. Maybe you used the wrong method when you measured. Maybe you got the units wrong, whatever. Maybe you made an error when you actually took the measurement. Or maybe you took the measurement fine, but when you recorded it, or later when you're putting it into maybe a spreadsheet to put it in a piece of research or something, maybe you just wrote it down wrong or something. That's a reporting error. Maybe it just got copied incorrectly. There's another type of error too. Maybe the element from your data set that you measured, maybe it wasn't measured incorrectly, maybe it wasn't reported incorrectly, maybe that's all good, but maybe the observation shouldn't even be there. Maybe it's not from the population that you're studying, so maybe it's from something else and got included by accident. And finally, well, if it's not one of those things, maybe it's just an honest-to-goodness extreme value. Maybe it is natural, but it just happens to be extreme. But it's a good idea, if you see an outlier, to check first if it's possibly a measurement error, a reporting error, or a population error. And let's look at some examples of this here. So we're going to use a box plot to do this. So let's say we did a study of heights of 5th grade students in a class, and then we'll do it in inches. And just as a reminder, 48 inches is 4 feet, 60 inches is 5 feet. These might be tall 5th graders. I have no idea. I just kind of made this data out of thin air to get a point across. But hopefully you're okay with all of this. So in this box plot, besides the outliers here, which we'll talk about in a second, it looks like the data ranges between 48 and 65. We have a median of 58, a lower quartile of 53, and an upper quartile of 60. So these measurements are all fine and dandy for us at least, and we notice we have 4 unusually big or small values. We have 72 inches, 140 inches, 42 inches, and 15 inches. So we don't have enough information to actually check whether these data points are a reporting error or measuring error or something like that. But we can just talk about possible reasons. For example, if we were taking measurements of 5th grade students in a class and we came up with a measurement of 72 inches, by the way, 72 inches is 6 feet, there's a good chance that maybe the teacher's height got measured and put in the data set along with your 5th grade students. So maybe teacher's height. And that is a population error. Since we care about 5th grade students, not about 5th grade teachers. So that observation got mistakenly measured and reported. It shouldn't even be there. 140, well, that's really, really big. So the best I could think of for that is maybe this is a measurement error. Maybe that this student got their height measured in centimeters instead of inches. So maybe height in centimeters. And that is a measurement error. We just measured that student incorrectly. Let's go down here. 15. Well, 15 inches is 1 foot 3. Probably not the height of a 5th grade student. So it's not likely that it's a measurement error. Maybe it is, but maybe it got recorded wrong. Maybe it was supposed to be 51 inches and just got, the digits got transposed. So maybe digits transposed. And that is a reporting error. It's not that it got measured wrong, it's just when it was recorded, you wrote it down incorrectly. And finally, 42. Well, let's say we did check if it was a measurement error, a reporting error, or a population error, and it turns out it's none of those. Maybe it is indeed just a student that's significantly shorter than the rest of the class. So maybe this is a short 5th grader. That's possible. So again, we don't have enough information to actually check these things in our study because we were just given this box plot, but we can kind of guess at some of these reasons, and we can go and check if we had access to the data. We could check if indeed these were errors, or it just turns out that they are honest-to-God extreme measurements.